The next, if you wish, philosophy in thinking about clusterings. So we've seen what I would call distance-based methods for doing clustering, where you define some distance function, and then based on the distance function, you define different kinds of ways of doing clustering, whether it's a k-center or a k-median or a k-means or what have you. And they all give you slightly different things, but they're all based on distances. And then we also looked at hierarchical clustering, which is in some sense a layer on top of any kind of clustering system, but in its bottom-up form is again based on distances. You have this idea of single link, complete link, whatever, and you link things up based on the distances. But today I want to talk about a way of doing clustering that some would argue is not even clustering at all. And some have argued that. I'll send you a link to an interesting blog post at this point. And it's what is called density estimation. Okay, so many of you may have heard of density estimation. And on the surface of it, it has nothing to do with clustering at all. The name is just about, well, estimating a density. But it turns out that one way to think about the problem of clustering is not to think about points and clusters and distances and similarities. But so I have these little buzzwords in the book for different types of clustering. So distance-based clustering is basically, I don't like you, then let's find a clustering. You can think of density estimation as we're all family. And here's what I mean by that. In density estimation, you're saying that things belong in a single cluster, not necessarily because they're close to each other in some sense, but because they overall form part of some kind of what looks like a cohesive whole. So any 2 points might be far from each other, but there's enough stuff in the middle that they all seem connected in some way, that they all form possibly elements from some distribution. So if you start off under that premise, that the idea of clustering here is not to group things that are similar, but to find groups of things that could be modeled by a single distribution of some kind, then what you end up with is density estimation as a problem clustering, as opposed to some kind of distance-based method. Okay?
That's how we perceive clustering also.
Sorry?
That's how we perceive clustering also.
Is it?
We are asked to look at some data and tell what the clusters are.
Yes.
And how densely they are.
But do you use density? I mean, I don't know. Maybe I sometimes would use proximity. So proximity and density are related, but they're not exactly the same. So you may be right. Maybe you look at clustering that way. Maybe I look. But yeah, it is definitely one way of looking. I won't say it's the only way we look at it, but it's definitely a way. And so if you are thinking from that perspective that I actually do have densities in my data, that I want to find clumps of modes in my distribution, then this is the way you might want to think about the problem, rather than just thinking about k-means. But it turns out they're not that far apart. It's not, in some sense, opposing views. And what I want to start by convincing you is that, in some sense, k-means is a density estimation method in disguise. Okay? And once you realize that, lots of other things, interesting things start happening. So let's look at k-means again. So if you remember, you have a bunch of points. What you want to minimize is some kind of objective function that looks like, for each point is equal to 1 to n. And for each cluster center, right, you're basically minimizing the sum of the distance. Let's see, distance of xi to cj squared. And if it's k-means, you can even rate this as. This is the k-means objective function. You're trying to minimize the sum of squared distances. And we had many reasons why we liked the sum of squared distances. There were certain arguments in favor of this thing we talked about. But let me give you a different way of thinking about this. Okay, let's forget all about k-means for a second. And let's think about distributions. In particular, let's think about Gaussians. So I'm going to write out a density function for a probability density function for a cluster. So I'm going to say I'm given some kind of center of a cluster. We'll call it mu. Call it mu I, the I cluster. And I now want to say that my cluster really is a Gaussian centered at this. And let's say it's all nice and simple. It's even though it's from the line, so I have a standard deviation. Let's say it's sigma I. If I had to describe what the probability density function is Gaussian as well, it's something like p of x. I'm going to write this in this form, given mu. So in other words, I'm thinking of a density, sampling a density over the space, but I'm saying, given that I'm thinking about the cluster I, with center mu I, right? Maybe I should write this as just I. Right? is proportional to, and I'm going to ignore scaling constants. I mean, you can all fill in the appropriate scaling constant for Gaussian, but basically it's going to be dependent on some exponential minus x minus mu y whole squared. And for now, I'm just going to pretend that the variances are all 1, just to make things even simpler. This is what it's going to look like. And the reason I'm being careless about writing this is because you're going to see in a second that the actual constants don't really matter that much. What matters is the form. So this is how I would describe the density of a point in this particular cluster. Right? So if I had, if I had one cluster that looked like this would be the density for that. Maybe I have another cluster that's nearby and it looks like this. And then there's another cluster a little bit further away, and it looks like this. Suppose I wanted to figure this out, right? I mean, I want to find these centers. Let's assume I know that they're all unit deviations. So the only unknowns here are these mu i's, which are effectively the cluster centers. And I want to find these cluster centers. And what I'm given are samples from this. And let's assume also for now, just to make these even simpler, that all of these are equal mass distributions. Right? All the clusters are equal size. And I'm allowed to sample from them. So you can imagine, say, I toss a coin, which gives me either one of black, red, or green. And then I toss another coin, say, okay, now that I'm in black, what is my probability of showing up? So I get a sample. So for example, I might get this point either by generating from this or from this. I don't know. I just get some point. So think of this as getting a bunch of y's. I get a bunch of samples. So I get a bunch of samples y1 up to y. Okay, these are my points. And now I want to figure out the cluster centers they came from. In effect, I want to cluster them. I want to find these groupings. Okay? So what might I do? So one thing I might say is, what is the, suppose I have a given guess for my set of cluster centers. I have some candidates. So I have some current mu I, mu1, mu2, and mu3. Right? These are my current guesses for where my centers lie. If I believe that to be true, where might I predict this y1 has come from? Well, in the absence of any other information, I might say, let's look at the maximum likelihood. Well, I know what the likelihood of y is. If y is given by this, right? So the probability of y coming from 1 is given by that, from 2, and so forth. What is the max likelihood? Well, it's convenient to take logs of things. So what's the max log likelihood? Well, if we take the log likelihood of this expression, so log of x minus mu I whole squared, we want to take the max of this over all I, right? I should put y there, because y is what I'm looking at. Do this calculation, the log cancels the x, the max becomes a min. Is this some else thing? What am I saying? I'm going to take the min over I, y minus mu I. But what is this operation right here? This is saying pick the closest cluster center as your candidate center. Right? What is that step? We've seen that step before. That's one of the steps in K-means. Right? Take the closest cluster center. And in some sense, you could think of this as, well, that minimize that function that you want to optimize. Or you could say, well, in fact, it's the argmax of the log function, if you have Gaussians. Okay, good. So you have that part. But now what? I've got these assigned, but I don't know if these are the right centers to begin with. So what do I do now? So now you can say, okay, I have points assigned to these clusters. What is really the correct set of clusters I need for this? Right? So again, I can do a likelihood. I can say, okay, so given my assignments that I already have from y's to the cluster centers, I can say find the best set of cluster centers over all mu1, mu2, mu3 that maximizes this total probability of x given the combination mu. How do you write a capital M in Greek?
M-O-N?
M for mu. Is it just M?
The
collection of all the mu's.
The Unicode phonetics would tell you that it's actually a different character, but
Sorry?
the Unicode phonetics would actually tell you that it's a different character, but it looks precisely the same.
Good. Because I'm not about to go look it up. So So this is the collection of all the mu's. You can think of that way. Okay. So, but now I want to maximize this over the choices of the mu's. Okay. So if I write down this function, right, I can say, okay, let me see if I can do this right. So I can write down this because of independence assumptions. I can write down this likelihood. So I'm going to put a log here, right? So it's going to be a log of the product of all the likelihoods for the individual points, right? So what I'm going to do is, it's going to be a log of product of the probability of any particular point given any particular mu. So xj mu I. And of course, since we've assigned points to clusters, we only care about points being pairs for which that point is assigned to that cluster. So we have this gigantic product over here of all points assigned to each cluster. So for example, if you had 3 clusters and you had these 3 points here, 1, 2, and 3, that's cluster A, and 4, 5, 6, cluster B, and 7 and 8 here, that's cluster D, you'd have some probability of the form, probability of 1 given A, probability of 2 given A, probability of 3 given A, so on and so forth, under this independence assumption. Of course, each of these now can be written in this form. Right? So now we can, so if we collect all the terms for any one of these functions, this gigantic product merely becomes a log of the x of minus sigma x j minus mu I squared for j assigned to I. Okay. And again summed over, well, product over all I. Okay, so there's one term for every cluster now. And again, if you take the logs of this whole thing, what do you get? You basically get a minimization where you now are taking log x max. You want to minimize the sum of xj minus mu I whole squared over all j assigned to I. But we know how to solve this as well. What is the mean that, what is the point that minimizes the sum? It's the mean, which is the second step of k-means. So in some sense, if you assume that your data was coming from a Gaussian, you could express the 2 steps of k-means, the nearest neighbor step and the finding the mean step, as some kind of maximization of a likelihood function, where the likelihood function only becomes defined because I have likelihoods, I have distributions. And so k-means is kind of a density estimation method, sort of, in disguise. And this is also, by the way, explains this folklore thing that k-means gives you spherical clusters. It gives you round things. Why? Well, it's trying to fit Gaussians. In fact, it's trying to fit Gaussians with unit variance. So it's not surprising that to try and find things that fit nicely in kind of some symmetric fashion. Okay? So this is just a kind of a teaser, if you wish, a preview of why we're looking at density estimation. It's because there are algorithms we actually use that look like they're distance-based, but can be viewed as density estimation in disguise, which brings up the bigger question of, can you think about density estimation in a more general setting? And how do you do clustering from that perspective? Okay? Any questions? So, how many of you are in Vivek's machine learning class? Okay, so you have those of you who raise your hand have the option of falling asleep to this lecture, because what I'm going to do today, which is the EM algorithm, he's going to cover sometime in April, I think, in his class as well. Or you could pay attention and learn it twice, and you'll know it even better than everyone else. It's up to you. And also, different people have different ways of thinking about EMs. I think it'll be helpful to see how I think about it, which is probably not the traditional ML way. In the way he thinks about it, it probably is. So you probably have all heard of this thing, the EM algorithm, or expectation maximization, or something like this. How many of you have heard that phrase? Okay, in some form or the other, you've heard this phrase. Good. You may have also heard that it has something to do with density estimation. That's something to do with k-means in some mysterious way. And so what I'm hoping to do today is explain to you this one algorithm, the EM algorithm, that is used for this kind of density estimation problem, namely finding out how a mixture of Gaussian, a mixture of distributions that captures your data. It's a much more general algorithm than that. It's used for any kind of what is called a missing data problem. So, but I'm not going to go into the details of that. I will try to keep it focused on clustering. But you should know that the EM algorithm is an example of a much larger class of methods. It's a very powerful method, so it's worth understanding. So let me explain it in terms of sort of a general parameter estimation problem. So imagine that you have, and we'll see why the name EM comes. So imagine that you have some kind of process. The process is parameterized by some parameters. Now, every time I say all these things, it might be helpful for you to map it back to clustering just to keep some context. For example, so I say a process generated by some parameters. Okay, what would that be for mixture Gaussians? What does that sentence mean in this context? So some kind of density that's generated by a system that has certain parameters attached to it.
Mean and a variance?
Sorry?
A mean and a variance?
You have mean and a variance, maybe multiple means and variances. And then the process would be what?
To generate the points? Or?
And by some sampling process, yes? And is defined by some distribution, maybe Gaussian. Oh, good. Okay, so you have some process, and it's generating samples, and there's some set of parameters theta. So you should think of theta as the vector of all the parameters you have, right? So there's some parameter theta that's generating this process. You don't know what theta is, okay? What you do have is observed data. So you have some observed data, y1 up to yn. So what would observed data be for a clustering problem in this language?
Points?
The points, the actual points you see. You can think of your points that you're being asked to cluster as drawn from some distribution, right? Some mixture of distribution. Okay. And there is some sense of what you want. You want some data x, right? And that's the complete description of your data. And again, for clustering, what would that be? What would the complete description of your data be for a clustering problem? I've given some process data, like y1 through yn.
The cluster centers combined with
The assignments here. So the cluster centers would be the parameters, but the assignments of points, which cluster does this point belong to, would be a complete description of the whole thing. So this is your x in some sense, right? Or you could think of x as really just y and z, where z is the cluster label and y is the actual point, right? We don't have that. All we have is the y. So that's what's missing here. Sorry, not the one making noises. Let me track it. No, I am the one making noises. Sorry. What I'd like to do is use the samples I've drawn to figure out the process and figure out the data. In other words, figure out the means and figure out the labels. Right? This is the general goal of a density estimation problem. Okay? And and so in particular, you also have some knowledge of this. You have some knowledge of how theta would generate the y's if you knew the theta. So this, for example, would be some functional form. And you also have some knowledge of this. Okay. Okay. So what you'd like to do is some kind of maximum likelihood estimation. You'd like to be able to say, okay, I'm going to figure out the maximum likelihood parameter given my data. And in general, since the maximum likelihood is a messy to deal with, you might say I want to determine the maximum log likelihood. Log is a monotonic function, so it doesn't change anything. It just makes sense. And in general, this can be a hard problem for you. It's hard to describe these things in a general sort of process. So what we're going to do is to break it down into some sort of simpler set of steps.
I have a question. What's the y?
So we think of x as the pair y comma z.
And
You
what
can think
is-
of it that way.
What is z?
Well, in this case, z would be like a cluster label. Y is the actual data, and z is the extra information. So x consists of y and other information that you don't yet know. So this is like a missing data problem. So the EM algorithm at a high level looks something like this. It says, okay, guess some form, some theta 0. You have some guess for your parameters. It could be random, it could be whatever you do. Okay. And once you have that guess, pretending that it's correct, you can construct the distribution probability of x given y and theta 0. Right? Because you have enough information to write down this expression. Okay? Basically saying this is what your missing data should look like given what you've already seen and given your guess for the parameters. Think of this as saying if I have points and if I have cluster centers, what might my cluster assignments look like? Right? So then you're doing this nearest neighbor again. But you don't actually do the nearest neighbor. You use this number to compute this interesting function. So define Q, we'll call it theta, theta 0. So it's a function of an unknown parameter theta, okay? Which looks like this. Is an expectation of, again, a log likelihood. So a log, a likelihood function of x given.
I have a question. Are you sure there's x there in the second step?
I'm not sure of anything until I finish writing it, then I will answer your question. Yes, you were saying?
Are you sure there's in the second step there's x?
Here?
Probability of x given y.
Yes.
Doesn't make any sense.
Okay.
It should be z. So you're trying to estimate z, right?
Well, are you saying this doesn't make any sense or are you saying it's redundant? I'm willing to agree that's redundant. I'm not willing to agree that it doesn't make any sense.
Okay, yeah.
So which one are you saying?
Redundant.
Okay. Yes, I agree it's redundant. But it's good to have it this way. Because you can't always break down x in terms of y and z.
It's like hidden.
Okay. So this is, I'm going to define this weird function. And let me explain what this function is. It is what is called it's a mouthful, it's a conditional expected log likelihood. Conditional expected log likelihood. And what it's saying is that, given that I know y, I've seen the data, given that I made a guess for theta 0, my guess for the parameter space, right? What new choice of the parameter theta? Or plug in a value of the new theta, and you get this expected log likelihood function. So this is a function that you're going to construct that somehow guides you to the search for the right new theta value, because you're going to try and maximize. Eventually, you're going to try and maximize this quantity. But you first have to construct this function. Okay. So this is basically capturing, what is the way in which you want to go from theta 0 to theta. And then step 4 is going to be to maximize Q theta 0 overall. Okay. And this is my new guess. So we'll call it theta 1. You repeat that. And the EM algorithm is called that because one thing that's a little different between what we saw with k-means and here is that k-means is like a sort of a non-smooth version of this. In the sense that this step here, instead of doing an expected value, we just said take the argmax, take the max log likelihood, and fix it as one thing, and then maximize the second thing. Here we're not doing that. We're actually computing a smoother function and then maximizing that to get the next value. Yeah?
Can you comment on what's the difference between kernel density estimation and like a Gaussian mixture model?
Should be asking Jeff this, not me. Let me think. What is the difference between kernel density estimation and a Gaussian mixture model? Well, I think that maybe in the mechanics there's nothing different, but in the purpose there's a difference. So let me explain. In kernel density estimation, your goal is to estimate some kind of multimodal density over the data, which could have many bumps in it. And you have these samples, and you slap down these kernels on them to give you some kind of approximation of the true density. In fact, you represent your density as this in terms of this kernel basis, right? You write k summation k of x minus mu I. You write this whole basis out and write this whole thing In mixture of Gaussians, in some sense, the problem is different. You expect, you know that there's a small number of Gaussians that is a basis for what you're doing, and you want to find that basis. So once you've come to the same question from these different places, you might end up doing something similar. But the fact that, for example, you have many, many cluster centers for kernel density estimation might change the game in some ways over what you're doing. You're not expecting to find these big blobs, you just want to find something that captures data. And the kernel density estimate is somewhat an approximation that you know in the limit gives you the right answer. We're not claiming that here, it's slightly different. So I think at a lower level, at a mechanical level, they're basically doing the same thing, but philosophically, you're thinking slightly differently. That's my guess, best guess. But you're right, that if you had a mixture of Gaussians with many, many, many Gaussians in it, you're essentially, you're doing kernel density estimation.
I have a question.
Yeah.
Can you write out this expectation?
This one?
Yeah.
I'm going to. So one thing that's nice about this is that you can show at this abstract level that this estimate always improves over time. You get a better and better estimate for this log likelihood function. So this will converge to something. There's no guarantee it'll converge to anything interesting, and this is true with k-means as well. So I'm not going to be able to say anything formal about what kind of result you get, just that it will eventually stop if you keep doing this over and over again. Okay. So what I'd like to do is, having given you this very high-level 30,000-foot view of what an EM algorithm looks like, try to put it now in the context of clustering and see what it looks like for a clustering problem. So what you will end up at the result is not k-means. K-means is a very weird special case where you don't do the expected value. What you'll get essentially at the end of this process is a kind of a soft version of k-means, where you end up not with points assigned to clusters, but probabilities of points being assigned to clusters, which is what you'd expect with actually a mixture of clusters. Okay, so that's the end game here, but we'll get there in a minute. So any questions so far before I go any further? Okay. So one point I want to mention is that it turns out to be useful, and we'll need this later on, is that when we're dealing with functions of this form, which we will for clustering, where you have this nice decoupled structure, you can actually simplify this expression. So I want to write this out in more detail and then simplify it a little bit. So by definition, we're doing this expectation. An expectation in a continuous space is some kind of integration. Right? So we're going to write this as, so let's say q theta 0 is equal to, so this gigantic integral, which you're going to integrate this function with respect to this. So basically, it's going to look like this. Log p x with respect to p x y comma theta d what? dx. Okay? And we already know that x can be written as y comma z, where y is given to and z is the unknown term, right? And this unknown term is these labels that we want. So what I'm going to do is I'm going to plug that in here just to simplify this expression a little bit. And it's going to look like this. And again, if you don't like seeing streams of algebra, which I don't worry, it'll all end in hopefully without too much pain and suffering. This can be simplified, right there. So you can write this as log p y z theta p of z given y. And the way of thinking about this is that this is basically another expected value. It's expected value of this quantity, right, with respect to this. So it's the expected value of the log likelihood of p y comma z given theta with respect to z conditioned on y. So this is my new Q function. I just want to bring this up because we're going to be using this in a few minutes. Okay. All right. So how do we apply this very vague abstract framework to do clustering? So we're going to start with a somewhat simpler problem, that what we have is a fixed collection of distributions. Okay, so I have some distributions. One could be, a Laplacian distribution centered at 0. One could be a Gaussian centered at 10. One could be something else. I don't care. But they are fixed. It's not. I don't have to look for the means of these distributions or do anything like that. Okay, they give it to me. All I'm trying to look for is what the relative weights are.
I have a question.
Yeah.
Is there a particular reason why they chose log?
It's just more convenient to work with logs. Logs don't affect your transformation, and
So
for
when you
maximizing
use
logs,
products,
you can just convert products into sums and
Sums.
everything is good. Yeah, that's pretty much why we always use logs in these things. Log likelihoods. In fact,
I
almost
thought
weird.
maybe there's some correlation. Something.
Well, in some sense, information theoretically, the log of the likelihood function gives you a unit of bits in some sense. So this, at least from a computational point of view, it seems more natural to me. Log of probabilities gives you bits, and bits are what you want to optimize. But that's a different perspective. I think there are different ways you can think about this. The laziest one is just that it's easy to work with. All right. So like I said, we're going to assume a model now where we have a fixed collection of distributions. So think of our distributions as P1 through Pk. I'm not even going to write them down because they're fixed. Right? There's no unknown regarding those distributions. All I do not know is how the weights are combined together. So in particular, my theta parameter, my unknown parameter, is actually going to be weights theta 1 to theta k. So I should think of my data as generated by the distribution. Let's see. Yeah. So for any particular y, the probability that y is equal to yi, the sample yi, is equal to the sum of theta j, pj, yi. In other words, what is the probability that you picked the jth distribution to generate yi, and then what is the probability that you actually generated yi? We take an or because any of your distributions had the chance to do this. Right? So for example, in this case here, you have V star equal mass with the half probability you pick black and with the half probability you pick red. And then once you've picked one of them, with a certain probability you'll pick that point in the middle there. So that corresponds to that total probability. Right? So this is the process that's generating my data. This corresponds to this thing. Okay, so that's the first step. And we'll assume that, obviously, that, and we just want to find them. That's the only goal we have, to find these things. Okay. And we'll assume the hidden data, the z's. So we have z, which is equal to z1 to zn, right? And zi basically belongs to 1 to q. So zi is a label for the yi. Right, like I said before. So we're saying if yi has a label 10, that means we drew it from the 10th. It really belongs to the 10th distribution. That's where it came from. Okay. So then, given that, what we need is this quantity. Right? So what is the probability of seeing a particular y and a particular z given the whole vector theta? Well, the probability of seeing that yi had label zj, right? So the probability of seeing yi and zj given theta is basically this one term. So it'll be theta j and j. Right? Because this is the conditional probability of seeing both of these things given that. So you're going to see this label, which gives you that, and you're going to see that, which is that. All right. So once you have that, the last thing we need is this quantity here. What is the probability of z given y and theta? Right. Well, this is where we apply Bayes' rule. Probability of zj given yi and theta. is equal to the probability of seeing zj yi given theta divided by the probability of seeing yi given theta. Well, thankfully, we have all these things. Right? So this is basically equal to theta j. I should have mentioned this earlier, that I've got now. I feel bad now. I see you guys all scribbling frantically. I have notes for all of this stuff. I should have given it to you earlier, but anyway. Some people like to write notes. Just I can't do it. Okay. So what the saying is basically is not very surprising. It's saying, okay, there's this total mass of this particular cluster. Right? The probability of this the probability of zj being a particular value j, given that you see y, is just this mass divided by the total mass. Again, not very surprising. And in fact, we'll even give that a name, just because we're going to be using it later. We'll call it alpha j. It's only a function of j. Okay? All right. Now that we've set up all these things, we're now ready to sort of do step 3. Write down this whole Q function that we want to optimize, to do the E step. Okay. So let's start doing that. So what's it going to look like? So this is what the Q function is supposed to be, this integral here. And you can just plug that in right there. Right? So this is going to be log of this expression, which is this, times that expression, which is that. This integral is really a sum because the range of my parameter z is discrete. It's just 1 through k. So it's this whole Q expression, right, is really just the sum of alpha j log what would it be? Theta j pj yi. So I should have probably put hats here, just to say that this is the current estimate that we currently have. This is the new estimate. Okay. Now, wait, I wanted an expected value of this. Did I get my? Yeah, okay, good. So now, if I want to maximize Q with respect to theta, I don't care about terms that don't involve theta. So I can really break this down as really an interesting term, which is alpha j log theta j, and an uninteresting term, which is alpha j log pj. This I don't care about because for maximizing Q, that's not going to affect me anymore. And now here's where things start getting interesting. It turns out, and you can prove this, if you want to maximize this quantity here, I don't know if you know what the answer to this question is. If you want to maximize this, the correct thing to do is to set theta j equal to alpha j. And what this is saying is that since alpha j is this kind of, if you think of this as a kind of a weighted sum, this is the equivalent of the mean finding step for k-means. That's like the second step, the M step if you wish. So this whole process of construct P, define Q, and maximize Q led us to the conclusion that given what we have so far, our current guess and our current alpha j, the next theta j is going to be equal to alpha j. And then that's going to go in here, and you're going to start this process all over again to repeat this. And so what this is saying is that you have some current guess for your values. You construct a weighted sum that represents the fractional importance of each cluster. And that's actually going to be your next guessed weight for each cluster in the cluster. Right? And that's what's going on here. And then you repeat this again. So it's a lot of machinery. But when you actually work on the details, it's not very hard. Algorithmically, all you're saying is that I start off with some guess for thetas. I compute these quantities, which I have the PG so I can do this. Right? So I get these alpha j values. And then I set it again, and I do it all. And so this works for a fixed collection of distributions. Of course, if you now have a collection of Gaussians, then this changes a little bit. Now you have more parameters to play with. You have the weight, you not only have the partition function here, but you also have the parameters inside. And so that's what I want to go to next. But this was kind of a warm-up to that step. So this is a good time to stop and maybe take a break for a few minutes to breathe and see if you have any questions about this. Normally I usually give people a break around a little bit earlier. I haven't been doing that of late, but so I think today's lecture I think it'd be a good idea to take some short break. Say about 2 minutes if you want to go get some water or something. Okay, I'm actually going to erase the previous one because I just want to keep this general framework up on the board. So again, like I said, I have notes for all this stuff. So it's a very nice, actually. There's a free book on the EM algorithm. So if you suddenly discover after this lecture that there's so much more you want to know about the EM algorithm, then there's a whole book of waiting for you just to read that. One thing I did want to say about this. Okay. All right, so we described how you might apply this general EM framework to learning the mixture weights of a collection of arbitrary fixed distributions. What I'd like to show you now is how you might use this to not only generate the mixture weights for the distributions, but the parameters as well, in particular for Gaussians of mean and the covariance. Okay. So again, for a Gaussian, we have two key parameters, or two sets of parameters, I guess, if you want to think about that, right? So let's say I have, again, k Gaussians. So for each Gaussian of the k, I'm going to have first a number wj, which corresponds to the weight. I don't want to use theta here because there are many parameters there. This is the fractional weight of the Gaussian, the size of the cluster, if you will, or the probability of picking that particular Gaussian to generate data from. But then for each Gaussian, you also have a mu parameter, and you have a covariance parameter, right, which is some kind of matrix. These are all, high-dimensional spaces. And so in general, you can write that the probability of seeing a particular y, given that you're in cluster J, is going to be proportional to, again, some x. But the x was a little bit more involved now. It's more like, let's see, let's make it this right. I always forget whether to put the inverse in this one. Yeah, so something like, there's a constant here. The -1 is the important part. The other part doesn't matter. Y minus mu I transpose sigma inverse y minus mu I. So before, let me parse this weird expression. Remember, mu is a vector. We're in some d-dimensional space. So y is also a vector. It's a sample. So y minus mu I is a vector. And this weird construction here is the matrix analog of okay? That's what's really going on. In general, though, you may have different covariant variances along different dimensions and cross terms, so you can't actually write it in this nice, simple isotropic fashion. You write this more general form. But it's really, I personally just like to think of this in this, just sort of squid it in and just process it. That's what's really, but it looks complicated, but really it's all this. Okay? So now we know what the distribution form looks like. So we have that first step here, right, as before. So now we have to fill in all the appropriate remaining terms that we need to start running the whole machinery for here. So once again, we can say that the probability of that y is equal to yi given the set of parameters, right, is going to be, and we'll call this expression, just call this expression phi for now. Yeah, let's call it p, let's call it phi. Just simple, because I'm going to be using it. So this is equal to summation wj phi yi given j. Right, well, as before, there's a certain probability of picking the jth density to generate your y, and once you have this certain probability of actually picking that y, this is what your expression looks like. Right, just like before. Okay, so you got that first term here.
Why they write probability y equals yi? Why just not probability yi?
Because probability is, you're saying what is the probability of a certain event? What's the event? Probabilities are always of events, right? What's the event here?
Yeah, so you're trying to make, you're saying y is the random variable
Yes.
and yi is the
Because remember, I want to compute expectations over things. I need random variables.
That's
So it's a more precise way of saying this. So these things are confusing after a while. Well, not that they're not confusing already, but they're more confusing. So, and once again, you can define this sort of hidden variable z's, and you can say what is the probability that zi is equal to j, right? Given yi and theta. We're going to give this a name because it's going to be used a lot, just like we had before. We're going to call it gamma ij. Okay. And as usual, it's going to be wj phi yi given j over this entire summation. I don't want to write the whole thing. Right? So it's this entire sum at the bottom. It's the same way we did before. The same Bayesian trick. It's equal to the joint probability of that. And these numbers are going to be important. These numbers play the role of the alphas that we saw in the previous example. And what this is going to tell us at the end is, what is the probability that point I is assigned to cluster J? This is the thing we want in some sense. Right? In a k-means clustering, we're saying point I is assigned to cluster J with probability 1. And we don't say that, but that's what we're really saying, probability 1. Here we're getting a lot more nuance. We're saying, no, 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 there's some probability of assigning to J, there's some probability assigning to J prime, and so on and so forth. So what you get with EM is a soft version of k-means. We haven't yet talked about soft clustering, and I'm not sure how much more we will, but the idea of soft clustering is that you don't commit definitely to one cluster or the other. You allow yourself to kind of vacillate a little bit. Maybe I'm in this cluster, maybe in that cluster. This is actually useful. It gives you a kind of a smoother landscape of clusterings. You don't have this jerkiness where you either have to go here or have to go there. And maybe for your problem, you don't really want that. You just want some sense of likelihood, right? And so this is one way to get that. Using the EM algorithm, you get these likelihoods. You may have also had a fuzzy CP, which is another way of getting it. So this is the important quantity. This is the thing we're going to have to compute. So in the process of doing this whole EM algorithm, we're going to compute the thetas, we're going to compute the gamma j's, we're going to keep iterating. And we're going to converge at some point with both the parameters and these. And that's going to be our final answer. All right, that's just looking ahead. So once you do that, again, you can do this whole boring thing of computing the Q. Right? So you say, okay, there's this Q function, and you write it as an expected, as an expectation of a log likelihood function, the y comma z given theta, subject conditioned on z given y and theta, and you write this whole expression out. We already have this term, we have the other term there. So you can write this out again as basically sigma gamma ij. Make sure I get the sigma over the right thing. Yeah, it's over j. P log, sorry, sigma log of this log of p y z. Which is basically just one of these terms, single one of these terms. And then you take the logs and you get this horrendous looking expression, and what you get at the end of that is that your Q, so let me be more precise, this is Qi for a single yi. And so the actual Q will be the sum of the Qi because of independence. And that will be basically equal to the sum over I, the sum over j of this entire expression. And okay, so now this starts getting extremely boring. But basically what happens is this whole summation breaks down into two parts. Okay? Because this log term has this and that together, when you take the logs, they separate out just like we saw before. So you're going to get one expression which is basically of the form, one of the terms in Q is going to be summation gamma ij log omega j, wj. And you're going to get another term of the form sigma gamma ij and a log of that gigantic expression. So there's going to be a minus, and there's going to be a minus half, and there's going to be a y minus by transpose sigma equals y minus by. And these are all parameters we need to estimate. So just like before, you can observe that the correct way to maximize this part of the quantity is to set these wage functions equal to the normalized gamma ij. So basically, you set nj equal to the sum over all j of gamma ij, which, as I said, if you think of gamma ij as the amount of contribution point I gives to cluster j, then the sum of the gamma ij should be the size of cluster j in some weird sense, right? If every point gave all of its mass to cluster j, then adding up these numbers would in fact give you the number of points in cluster j. But it's a fractional value, it's like a relaxation, so there's some kind of fractionality too. But this sort of, morally speaking, behaves like the size of the cluster. That's why I'm calling it NG for now. So what this is giving you is that the gamma ij's give you the size of a cluster, okay? And those numbers basically show up in there. And minimizing this expression gives you the standard k-means objective that you have to sort of basically find the point that minimizes the sum of square distances, and you get the mean to be weighted by the cluster centers. So you basically get the new mean mu j prime to be equal to the average this should be, what should it be? Yij, right? Yeah, Yij. So what this is saying now is that if I want to find the mean of a cluster, I take the average of the points in the cluster. But every point is not really in that cluster, it's only partially in that cluster. So you take the appropriate average. So again, the point here is that all this derivation gives you what is a very meaningful way of computing the mean, a generalization of the normal k-means. But now you have contributions of points to clusters, so you have to attach that as well to the whole process, and this is the size of the cluster. And then once you want to compute the mean, you want to compute the covariance matrix you get. This actually also has a very nice form. It basically, again, is a weighted covariance matrix. So it's the weighted sum of gamma ij, the covariance matrix of the y minus mu j is assigned to. So you take all the vectors assigned to a particular thing with a particular weight, and you construct the covariance matrix of these other vectors, and the sum of that is your entire covariance matrix. And again, all of this follows pretty much directly from doing the calculation. You do the minimization here, do the differentiation here. It's all very simple, and it's all sort of works out. It's tedious, but it's not hard. And so once you have these three updates here, right, along with this definition here, right, you are now ready to do the iterative process. So you start off with a guess, you get the gamma ij's from this formula, you go through this whole thing, you get new guesses for these parameters, and then you start over again. One back and forth, back and forth. This gives you a soft cluster. So this is the EM algorithm as applied to a mixture of Gaussians. And again, there's nothing particularly special about Gaussians here. As long as you have some reasonable functional form here, you will be able to solve this whole thing. How exactly you solve this, how you do minimization, depends on the form of the distribution, but there are different ways you can do this. As long as you are able to minimize that kind of expression, which is true for these Bregman divergences and not just for Gaussians, you can actually run the EM algorithm for all of these different things, and you will get some answer. Again, I cannot guarantee to you what the answer will be, but you will have some answer that will terminate. Will give them local optimum. And this is a very popular algorithm for doing mixtures of Gaussians. If I have data that I believe comes from a mixture of k Gaussians, then I can do this. Again, I still need to know what k is, which is a different problem. But I don't need to know anything else. I can assume nothing about the means. I don't have to assume anything about the covariance matrix. Of course, how long it takes to converge will depend on how much data I have and all these things. So it's sort of a good heuristic, but it's somewhat unsatisfying. Any questions? Yeah.
Everything on the board, which ones are Qs and which ones are Ks?
Good point. You better? Everything else is there.
The lowercase theta look a bit like the Qs.
No, they do, don't they? Yeah, especially Dengin Man. It's probably with LaTeX versus writing. In LaTeX, it's very clear which is what. Not here. And that's why once we got to the EM, it's probably good to stay away from thetas altogether. So there are very few examples. So in the general sense, unfortunate choice of notation. Okay. What I've been discovering over the course of teaching this class this semester is something somewhat interesting, that for every single clustering method I've described, there is a really good heuristic that people love that has no formal guarantees. And there's a slight tweak to that heuristic that more or less looks the same and has guarantees as well. We've seen this for k-means in particular. We've seen this for hierarchical clustering. And in fact, something like this is true for EM as well. In the sense that if you want to learn a mixture of Gaussians, okay, and you want to prove something about what you've learned, it turns out that you can do something very much like EM. In fact, just 2 rounds of EM. And you can prove that you will actually reconstruct the correct answer. Okay. And so there's been a whole line of work on this topic. And the flavor of this work is of the following form. Let us assume that all the centers of the Gaussians are separated in some form. They're reasonably far apart. We need the reasonably far apart because if two things are really close, you can tell it's going to be really hard to disentangle them. When you take a particular sample, how are you going to tell if it came from one or the other? It's really hard. So you want to assume they're somewhat far apart. Under the condition that they're somewhat far apart, I'll give you an algorithm that will correctly reconstruct the right answer. Okay? And then over the years, what people have done is push that boundary of how far apart they need to be less and less far apart. Right? So the first algorithm, they had to be, this algorithm would only work if the centers were here. The next one say, well, they can kind of be here, kind of here, kind of here. So now kind of we're much better. But one of the first of these is basically an EM variant. The other ones got more complicated. But the first one is just like a simple modification of EM, which is actually quite nice because it also brings in k-center clustering as well in the process. So I just want to describe the algorithm to you. I won't give you the analysis. It's a bit, again, technical. But the basic idea is not that hard. So first off, let me describe what it means for things to be separated. Right? So we have to give the right units of measurement here. So in particular, what we're going to say is the following. Let's take 2 means. So we have mu and mu prime. Right? We will assume for now, this is again an assumption that has been worked on over time, assume these are all isotropic Gaussians, which means that their covariance matrices are symmetric. Right? There's no extra variance in any one dimension or the other. And I believe, let me check this. Yeah, so let's assume even more strongly, which is again an assumption, that all the covariances are the same. So they're all equal. So this is really a simple version of the problem. Nevertheless, let us assume that so let's say the common covariance shared by them is C, and let's say the distance between these 2 Gaussians, right, is at least C times square root of it. So why is that? So it turns out if you're dealing with, no, wait, that doesn't make sense. C cannot be that. Hold on. No, sorry. Yeah. I should say, let's assume their deviation is, let's say they have different deviations, sigma 1 and sigma 2, but it's isotropic. And let's say the distance between any 2 centers is greater than or equal to C times the max of sigma 1 and sigma 2 times square root. And the reason you want to say this is the following, that if you think of how you measure distance between 2 Gaussians, you may have heard of the 1 standard deviation test, 2 standard deviation test, and so on. That's because you could actually quantify in a scale-free way how much probability mass is under a Gaussian in terms of units of the variance. That's why the variance is important. If you don't know the variance, then you don't really know what it means to capture 90% of the probability mass or 80%, 70%. But once you have the mean and the variance, you can do this, which is why we always say things like x minus mu squared divided by sigma squared. You're basically saying that the only unit that's important here is units of the variance. Okay. So it's always in terms of that. The square root d comes from the fact that you're dealing with this thing in d dimensions, and it's a normalizing term you need for that. But what this basically saying is that if you look at a Gaussian at sigma 1 around it, roughly speaking, it's going to be, all its mass is going to be concentrated in a shell somewhere around here. That's distance, something like sigma 1 square root d. Okay? And for this Gaussian, it's going to be another shell here, something like sigma 2 square root d. So there's a very weird property of Gaussians. You think of a Gaussian as a blob that's smearing out, but actually in high dimensions, most of the mass of a Gaussian is in a thin shell at that radius. It's almost like a hard ball instead of a smooth, because of again, the weirdness of high dimension spaces. So if I'm saying this distance property exists here, I'm saying these two walls are kind of far from each other. Right? They're well separated. And intuitively, if clusters are well separated, we should be able to find them. And it should be pretty easy to tell for a given point whether you're from one or from the other, because the clusters are well separated. If they were overlapping, we won't be able to do this. But here we should. And this is a theme that runs through a lot of clustering algorithms. I should mention, by the way, I forgot. We have a faculty candidate coming next Monday and Tuesday. I'm not going to say who because we're on camera. But if you look at the announcements, they send out a colloque. You will and that person does a lot of work related to clustering. I will send out a mail on Canvas announcing the details of the talk. A lot of the work there is going to be related to things we're talking about here, about clustering and how to improve problem clustering. So getting back to this point, let's assume that I have an input where for every pair of centers, this property holds. Okay, so they're well separated. And the question is now, can I actually compute the true centers in a reasonable amount of time with a few samples without having some massive algorithm that doesn't guarantee? And it turns out it's actually very easy to do. What you do is, and you can assume, by the way, they have non-uniform weights. So what you do is step one is your first round of EM. You sort of initialize everything to equal weights. So 1 over k. And run EM for one round. Just one round. So you're just holding one time. So what you're going to get are new weights, means, and assignments. Right? So you're going to get cluster masses, the gamma j's and the nj's you're going to get. Then a middle step where you are not sure this is EM. So the middle step is eliminate all clusters with small mass. Small is some threshold that you have to set based on the algorithm. So again, it's a detail. So things that are very small. And what that means is that just remove those cluster centers and put those points back in the common pool. Because you don't treat them as independent. Okay? All right, that's the next step. And then what you do is oh, okay, sorry, I made a mistake here. What I should have said was initialize the equal weights of 1 over L, where L is equal to k log k. So in other words, start off with more centers than you need. So initialize L roughly equal to k log k random centers and uniform weights for all of them. Run EM for one round so they get these k log k clusters. Eliminate clusters with small masses, which are tiny clusters, and so the nj is very small for these clusters. They're not somehow important. Okay. And then for all the remaining centers that you have, run k center. The Gonzalez k center algorithm, do you remember that one? You just pick any point and then pick the furthest neighbor and the furthest neighbor and the furthest neighbor on the L centers. Okay? So now you have actually k centers left. You just pick k center. And then 2, run EM again. 1 run. So there's a bit of black magic going on here. But the basic idea is that if clusters are far enough apart, and if you choose, okay, so how many of you have heard of the coupon collector problem or remember any randomization? So if I have k things and I want to guarantee to sample all of them, I know that with high probability I need k log k samples. Because then with high probability I'll pick at least one representative from each cluster. So what's going on is that I have my k buckets for my individual clusters, right? I want to make sure I get a rep from each of them. So I pick k log k things at random. So I know at the end of this process, with high probability, I have one rep from every cluster. So now I run EM and stuff happens. If I have 2 points in the same cluster, they're all going to get much less cluster mass than anything else is going to get. So I can throw them away. And when I run the k center now, I only pick things that are distinct in different clusters. then I run EM again one more time to clean them up. So this is a very hand wavy. This is not telling you anything even remotely close to why this should work. But the intuition again is that if things are far enough apart, it's very easy to tease out which point should belong to which cluster. And one round of EM is going to be enough to give you a clue, and the second round of EM is going to be enough to clean up your mess. And so at the end of this, you could prove that if the centers were originally separated by enough, and you run this process, you are guaranteed with high probability to get the true cluster centers at the end of this. So it's a modification of EM, under a certain assumption about the data, but you now get a formal guarantee of running time and of quality. And there are many, many extensions to this algorithm as well, like I said, that improve this assumption by quite a bit. So there's a lot of work now over the past many years now on how to get the same thing. Yes?
Does the extension decrease the effect of dimensionality?
I don't know if they decrease the effect of dimensionality, but they can improve all these thresholds. There might be some square. See, the thing is, the square root d is kind of a unit of measurement. You can't really get rid of that too much. But I don't want to say more because there's some new ones that are extremely esoteric that do weird things with dimensions and k and solve these systems of algebraic varieties and stuff. It gets very involved. So I'm not completely sure.
Because the effect of d here is, it's pretty substantial.
Yeah, but see, in some sense,
Yeah, no,
you
we-
can't help that in high
yeah.
dimensions. Yeah, that's the thing. That's just it's a unit of measurement almost. So again, this theme that it recurs, right? That there is a heuristic that's very popular, and there's a slight tweak to this that actually gives you guarantees as well. And this happens a lot with clustering. I'll be talking about this another thing, spectral clustering as well. When we get to that. But that's all I want to say about density estimation, and we'll move on to other topics next week. Any questions? So do you have any thoughts about the whole idea of density estimation as clustering? So again, I'm going to send you a blog post which argues that density estimation is not in fact clustering. It might be interesting to look at it and sort of see what you think about it. Are there any questions right now about whether you think there's even any controversy about it? Whether you think, oh yeah, of course it's clustering, or of course it's not clustering. What do you think? So one perspective that I have is that somehow mixture of Gaussians is it's almost like a labeled clustering. Whereas in a lot of the clustering things we've seen, you have no identity for the labels. Here you're getting much more. You're not just getting the gamma ij's which tell you which things are assigned to, but you're also getting names of clusters with specific mu's and sigmas and they have some context. And one can argue you're actually getting a lot more from this problem.
It's a harder problem.
It's a harder problem.
Yeah.
That's true. Yeah, you are definitely solving much more. You're getting much more information, so it does seem a lot harder because you could get clustering without getting any of this stuff.
But we don't know anything now how this handles regarding the outlier. I think this totally screws up, right?
Well, it depends on the likelihood function. In fact, because you're dealing with these exponential families, they will handle outliers in a much more graceful way than something like k-means would, because they can basically assign that point to a cluster with very small cluster weights. So one of the reasons why EM is better at dealing with outliers is because it can be smoother about what it does. With k-means, you don't have luxury. Either you have to put it in there or put it there. You have no choice. Here, I can fudge my assignments. Yes.
So I find it odd that why would we say this can't possibly be clustering? Why would we even want to say that?
You like to read how the blog post work. I mean, I don't agree with that, but it's an interesting perspective. So I taught this class 5 years ago, and he was in the class that day. We had a big argument, and as a result, that he wrote this post. And so I think it's good to have that perspective. The thing is about what is it you're trying to find. If you're trying to find an assignment, then you're doing clustering. If you're trying to find this density, you're defining a density, and is it the same thing as finding a clustering? I mean, I think there's something to be said about what exactly you're looking for.
Well, if you find, if you have soft clustering, then you can get to hard clustering just by using the ones that have the highest probability.
You could, that's one way of doing it, or you could take a random coin and toss it. There are many ways you could convert soft to hard. That's not the only way.
Oh, okay.
Yeah. So, for example, right? I mean, this is the whole, I think, discriminative versus generative view of the world, right? Are you trying to make a prediction, or are you trying to describe the universe? With density estimation, you're trying to describe the universe in some way. With a lot of clustering, you're just trying to make a prediction. And depending on your problem, maybe you just want to make a prediction. Maybe you do want to describe the universe. Right? So I think philosophically there is a difference there.
Yeah, but it's only philosophical. In practicality, it's splitting hairs. I mean, you can use both interpretations to make a prediction.
Except that prediction is weaker in a strict sense, right? Because once you have a generative model, you can predict, but prediction doesn't give you a generative model.
Right, but clustering in some sense is just the prediction. I mean, it's a, I mean, k-mean still gives you a
nearest
description
neighborhood. Yeah, description.
of what your space looks like. So I'm
Right, so you can predict a new point by doing nearest neighborhood.
right.
Yeah, yeah.
But it also tells you, okay, what does this space of data look like? And it's you don't need pure generative to say that.
Yeah, but I think
But,
that the folks who like generative views, which is this basically, this is like generative clustering. I think the folks who like this will say that I do want to know more than just a prediction. I want to understand the universe because tomorrow I might want to do something else with it.
But there are big
And so the data is a lens on getting that universe, which is important for more than just clustering. I think that's what they would say. And I think to some extent that's right. It again depends on what you want to do with it. Right? If you only want predictions, then you're good. That's fine. But I mean, it's like the Bayesian view. The Bayesian view gives you a distribution over outcomes instead of picking the one outcome, which is the the max likelihood outcome. So that somehow it's better that sense. You get more information. You need more data to do it, but you potentially get a richer universe.
I don't know. It seems like this is like one more thing in the laundry list of things that Bayesians like to say claim is, I guess, is special about Bayesian approaches.
So I'm not a Bayesian, so I don't claim to be able to defend their point of view. But I have learned over the years to not dismiss it as much as I thought I should.
Well, of course not. I mean, there's Bayesian approaches that are great for a lot of different applications.
Yes.
But I find this philosophical hair splitting kind of.
Well, if you want to do sort of proof by market share, Google uses a lot of Bayesian.
Yes.
Yes, you're saying.
But the underlying problem with this is that we haven't assumed before is that we know what's the underlying distribution up to
In a generative world, that's how it always is, right?
Yeah, but it's not from practical point of view. You don't know what's underlying this distribution. How could you assume that it's Gaussian? Okay, you can
Okay,
say,
so maybe you're a Bayesian. You say you're right. You don't know, so let's put hyperparameters on this.
no, I know.
So there are ways to
up-
weaken your assumption.
That's why I said up to a parameter.
Yes. So that's what you're doing. You're up to parameters, right?
Yeah, but it's still not good enough.
Because
Well, you cannot. I know Bayesian a little quite a bit, but I know exponential function.
no, I
Exponential family of
think the
functions,
argument that none of these methods are perfect is a valid one. The question is, what can you do with what you have? The more complex the model, the harder it gets to do inference. Bayesian inference is very hard.
Yeah. No,
This is
that-
easier. So there's always this trade-off between how rich your model is and how hard the inference is. And you always choose a sweet spot in the middle there, right?
Yes, of course. But the initial question was, how do you compare this against what we've seen before, right?
Yes.
And that was the initial question. We said they were assigning points, and we were having metric
Yes,
space.
yes,
and
yes,
then
yes.
We went to Euclidean, and we haven't seen anything about distribution
Yes.
of the data.
Correct.
But now we made very, very strong.
Yes.
Which is distribution of the data. Of course, there are parameters up, down.
Sure. It's a different perspective on the problem. That's what I'm trying to say.
You need
When
to know much more about the problem.
Sure,
so
but
that
maybe you
can-
do. And then so
Yeah.
if I did know more about the problem, my distance-based methods would be insufficient. I find them very lacking.
Yes.
And so this is another tool in your toolkit when you're doing clustering to say, if I know more about my problem, here's another thing I could do to get clusters out of it. And that's all I'm trying to do in this class, give you tools to say, depending on what my problem looks like, here's a tool I might be able to apply. I don't want ever to claim that you should use this tool or that tool or that tool, but you should know when each tool is applicable. That's all. All right, see you all next week. So.